binary search, the problem reads as follows. Given a sorted integer array nums of n elements and a target value, write a function to search target in nums. If target exists, then return its index, otherwise return -1. So in the example here, 9 exists at index 4, so we return it. In the next example, the target value 2 does not exist. This is addressing the clause where the target value is non-existent in the array. So we return -1 as instructed. Now I would like to demonstrate how the algorithm plays out. So I have two pieces of input, target equals to 44, and an integer array in ascending order. And it is required that the array be sorted to perform binary search. Now, as a courtesy, I have written down below index numbers of the elements, and I have labeled start, end, and mid. So start and end are basically our search space. So that the start here is 0 because arrays begin with 0 index, and end is whatever the last element, its index is the end. And I have computed the mid here, and the formula for it is start plus end divided by 2. So we have a start of 0 and end of 5. So adding them, 0 plus 5 is 5, divided by 2 is 2.5. 2.5 is a decimal, which would serve as an invalid index value, so we would have to round it down to the nearest integer, which is 2. So that gives us the midpoint. So midpoint serves as a point of comparison throughout our binary search algorithm. So it's very critical that we have a midpoint to start with. Now, at the heart of the algorithm is the divide and conquer strategy. What I mean is that every time we calculate the mid, what we're basically doing is, depending on how our target value compares to the mid value, we are essentially dividing our search space in half each time until we get to our target value, if at all the target value exists. And if it doesn't exist, then we return something as a problem statement might instruct us to. Like in the case LeetCode tells us to return -1 if it's non-existent. But if it does exist, eventually the mid will equal to target. And why don't we start with the algorithm, and you'll see what I'm talking about. So the questions that we ask are in this fashion. So starting out now, I have calculated my midpoint, which is the index 2, whose value is 10. So mid's value 10, does that equal to target of 44? No. If it had, we would return the mid, which is the index value 2. Anyways, so when we know the mid does not equal to target, it either has to be the case that mid is less than target or mid is greater than target. And as you may notice, mid in this case is less than target. The mid, whose value is 10, is less than 44, which is the target. So whenever we meet either of these cases, what happens is that we have to alter our search space. So what I mean is the 0 to 5, this is the search space initially. So because we know that the comparison of mid and target, since we know our mid value 10 is less than target, what that means is we have to be looking in the latter search space here, 3 to 5. So what we say is, okay, since this is not part of my search, I don't need to start from here. I'm going to recalculate my start. So that's what we're doing here. Whenever mid is less than target, we recalculate the start, which is start equals to mid plus 1. So we say, okay, I'm not interested in 0, 1, 2. I'm going to start with here, with the next space. So I would do mid plus 1, which is 3. So start is now 3. So our new start is 3. I'm just going to abbreviate S equals to 3. So every time we alter the start or the end, we have to recalculate the mid, because mid is contingent on those two values. So, and if it were the case that my mid was greater than target, then I would alter the end, which would be the case that, oh, my target is less than my mid value, so I have to bring my end to the former place, to here basically, because what's the point of looking at greater values when I know for a fact that my target value is less than my mid? So that would be the logic there. But anyways, we know that mid is less than target is applicable in this example case. So I have recalculated my start to reflect mid plus 1, which was originally 2. We had a mid of 2 plus 1 now is 3. So the start is 3, and we have to recalculate the mid with this starting value, which is 3. So let's do that. Now mid is start, which is 3, and end, which is 5. So 3 plus 5 divided by 2 yields 3 plus 5 is 8, divided by 2 is 4. So our new midpoint is 4. Box it 4. So whenever we have a new found midpoint, we have to start out asking with the initial question: does mid now equals to target? Well, the value of the index 4, the element, is 23. 23 does not equal to 44. So then we have to ask our follow-up question. So mid is less than target still. So mid, which is the value 23, is less than the value target 44. So then we have to recalculate the start again. So mid was previously 4. 4 plus 1 is 5. So that gives us a new start value, which is 5. Start equals to 5. So when we have a new start or end, we have to recalculate the mid. So now mid would be 5, the new start value, plus the end, which is 5. Notice that at this point, we have come to the end of our array, which is at index 5, where the start and end both happen to be the same. So 5 plus 5 is 10, divided by 2. 10 divided by 2 is 5. So 5 would be our final and last index. Okay. I'm just gonna give it like a flower shape. Okay. So now we have to ask our question. Mid equals to target? Hey, it does. We have found our target value. So as I had mentioned earlier, the algorithm works in such a way that each time you have so you initially do have a mid, and that serves as a comparison, but from that point, from starting, what we have done essentially by picking a midpoint is that we have divided the array in half. And every time then and therefrom, we're further dividing the array in half. So each time we're dividing the array in half until we meet the target value. So this is essentially a divide and conquer strategy playing out in binary search algorithm. So we have found, and I purposely picked the last element just to show that this is how it would play out. And in the case the target hadn't existed, then we just return -1 as the problem had instructed us to do so. So I hope this makes sense. I think it's very intuitive. Like if you think about when we look through a dictionary, we don't flip every page until we come across the word we're looking for. It's alphabetized, so it is sorted in that sense. So then you really like start from like a midpoint, like let's say letter M, and then you see where, depending on what word you're looking for, you would go either in the former first, the former part of the dictionary, or the latter. So binary search is very intuitive, very human-like, and it's very useful. Anyways, the complexity analysis, which is the space-time analysis, the time the average performance of binary search takes is O of log n, and the space or the memory that this algorithm would take is O of n. Now I'm gonna run the code here. So there you go, we have a target input of 9 and it exists at index 4, so that's what the output is and that's what was expected. Now before I submit it, I just want to explain. I have this initial validation, which is nums.length equals to 0. If that's the case, which means basically we're given an empty array, then we're going to return -1, because how can you perform anything on an empty array? Like, you cannot perform binary search in an empty array, so we return -1. And the algorithm is basically how I had demonstrated. You have a starting point and an ending point, which I have defined as start equals to 0 and end is nums.length -1. And then while start is less than or equal to end, and in our example start and end had equal to each other, so therefore you have the less than or equal to. And then we calculate the mid after we had defined start and end. So mid is start plus end divided by 2. And if you notice here, I'm using math.floor, which is a helper function which helps to round down a decimal integer to the nearest integer. So because array indexes cannot be a decimal value, we have to round it down to reflect the nearest integer. Anyways, as I had mentioned in the demonstration, after we have found these three values, which is start, end, and mid, we have these three questions, first of which is nums of mid is equal to target, and that's the best case scenario. When it does equal each other, the nums of mid and target, then we return the mid. Mid is the index, and that's what we return. Otherwise, it would be either of these two cases, that nums of mid would be less than target or greater than target. And in our case, nums of mid was less than target. So we would alter the search space to change the start from 0 to mid plus 1. And then it indicates that nums of mid is greater than target, we would alter the end to reflect mid minus 1. So in the case nums of mid is less than target, what that means is our mid value is actually less than our target value. And in the other case, nums of mid greater than target, what that means is our actual target value is a number less than the mid value. And in the case that neither three of these conditions are met, that means we return -1, which basically reflects that the target value was not found in the array. And let's run the code. There you have it. Runtime 76 milliseconds, faster than 89.78% of JS submissions, and the memory usage is 42.3 megabytes. So I hope I was helpful, and if you have any questions, comments, please leave them below. I'll be sure to get back to you on that. And if you found me helpful and relevant, please do subscribe, as it really helps me generate more such relevant content and more often. Thank you.